Let's talk about a theory that completely rewrote the rulebook for the universe. I want you to forget everything you think you know about gravity as some kind of force that's, pulling you down. Instead, what if I told you it was the actual shape of reality itself? That space and time could be warped and curved by the sun, the Earth, even by you. Well, that is the incredible story of general relativity.
But before we get into the deep stuff, let's start with a really modern problem. Okay, imagine you pull out your phone to get directions, but that little blue dot, the one that's supposed to be you, well, it's actually 11 kilometers away from where you're standing. And every single day, that error would just get bigger and bigger, making GPS totally useless. So what's stopping that from happening right now?
Believe it or not, the answer is a theory that Albert Einstein dreamed up over a century ago. It's an idea so powerful, so precise, that the satellites orbiting our planet have to account for it every single second of every single day just to keep working.
That's right. You have a real-world, working application of one of the most mind-bending ideas in all of physics sitting right there in your pocket. So how on earth does a theory that old keep your modern life running smoothly? Well, it all comes down to this kind of cosmic battle against time itself.
Okay, so here's the deal. There's a cosmic tug-of-war happening. First, those satellites are moving incredibly fast, and Einstein's special relativity tells us that the faster you move, the slower time ticks for you. For the satellites, that slows their clocks down by about 7 microseconds every day. But, and this is the big one, they're also way farther away from Earth where gravity is weaker, and general relativity says time actually speeds up the farther you get from a massive object. This effect is way stronger, making their clocks run faster by 45 microseconds a day. So you do the math, they gain a net 38 microseconds every single day. If we didn't correct for that tiny little drift, the whole system would fall apart.
So where does an idea this radical even come from? How did Einstein figure this out? Well, it all started with what he later called the happiest thought of his life. It was a simple moment of insight that honestly changed everything.
For hundreds of years, physicists had two totally separate definitions for mass. You had inertial mass, which is basically how hard it is to push something to get it moving, and then you had gravitational mass, which is how strongly gravity pulls on it. And the weird thing was, for any object you could possibly measure, these two completely different ideas always gave you the exact same number.
Even Sir Isaac Newton knew about this. He saw it, he measured it, but he had no explanation for it. He basically just shrugged and called it a mysterious coincidence. And this mystery just sat there for over 200 years until Einstein came along and started thinking about it in a completely new way.
And this is where we get to his famous thought experiment. All right, imagine you're in a sealed box, no windows. You drop a ball and it falls straight to the floor. Now, here's the question. Are you sitting still on the surface of Earth, feeling its gravity? Or are you floating in deep space inside a rocket that's accelerating upwards at exactly 9.8 meters per second squared? And here's Einstein's brilliant insight. There is no experiment you can possibly do inside that box to tell the difference. They are physically identical.
And this idea gets a name, the equivalence principle. It's not just that gravity and acceleration feel the same. For all intents and purposes, they are the same. This one simple, powerful idea is the absolute bedrock of general relativity.
Okay, but if gravity and acceleration are really the same thing, that leads to a truly staggering conclusion. It means gravity isn't a force pulling things at all. It has to be something else, something much, much weirder.
I want you to go back to that accelerating elevator. Let's say you shine a beam of light from one side to the other. Because the elevator is moving up, while the light is traveling across, the light beam is going to look like it's curving downwards, right? But wait, if acceleration and gravity are the same thing, then that means gravity must also bend light. And here's the kicker. Light always takes the shortest possible path. So if its path is curved, it can only mean one thing. The very fabric of space and time that it's traveling through must itself be curved.
And that is the absolute essence of it all wrapped up in the famous Einstein field equations. You can think of it like this cosmic dance. Matter and energy, like our sun, tell space-time how to curve, and in return, that curved space-time tells matter, like the Earth, how to move. The Earth isn't being pulled by the sun. It's just following the straightest possible path through a reality that's been warped by the sun's presence. Mind-blowing.
Okay, so this is a beautiful, wild idea. But a theory is just an idea until you can prove it. And the first big test was going to require a total solar eclipse, a couple of very brave British astronomers, and a journey to opposite sides of the world during wartime.
The timeline here is just fascinating. Only 4 years after Einstein published his theory, Sir Arthur Eddington leads these expeditions to test it. The results leak to the press, and overnight, Einstein becomes the most famous scientist in the world. But the story's not over. Decades later, a huge controversy erupts, accusing the original team of basically cooking the books. And it wasn't until 2021, a full century later, that a new analysis of the original photographic plates finally settled the debate for good.
So what made this test so brilliant was just how clear-cut it was. There were really only 3 possible outcomes. 1, starlight passing the sun doesn't bend at all. 2, it bends by the amount that good old Newtonian physics predicted. Or 3, it bends by exactly double that amount, which is what Einstein's radical new theory predicted. It was a showdown, and there was no middle ground.
And here it is. This is the data that changed the world. The 2 teams got measurements of 1.98 and 1.61 arc seconds. I mean, look at those numbers. Both of them are right on the money for Einstein's prediction of 1.75, and they're miles away from the Newtonian value. The verdict was in. Einstein was right.
But then, in 1980, this paper just drops a bombshell. 2 philosophers of science, Ehrman and Gleamore, went back and looked at the original data. And they argued that Eddington's team had thrown out a 3rd set of data that didn't fit Einstein's theory, basically accusing them of confirmation bias. They said this whole thing undermined the ideal of scientific objectivity.
And that accusation really stuck for decades. It's in a lot of textbooks. But a super rigorous reanalysis in 2021 finally cleared things up. It turns out that the 1980 paper made a basic statistical error. The original 1919 team's decision to throw out that noisy data wasn't bias. It was just good, sound science. Eddington and his team had been right all along.
Okay, so that first test was about space-time being curved by mass. But Einstein's theory predicted something even weirder, if you can believe it. He said that a massive, rotating object, like our Earth, should literally twist and drag the fabric of space-time around with it as it spins.
So how do you test that? Well, NASA launched Gravity Probe B, and to test this frame-dragging effect, it carried 4 of the most perfect spheres ever made by humans. They were quartz gyroscopes, so perfectly round that if you blew one up to the size of the entire Earth, the tallest mountain on it would be less than 3 meters high. They were the most perfect reference point imaginable. And after years of incredibly careful analysis filtering out all the noise, they found it. A tiny, almost imperceptible drift of negative 37.2 milliarc seconds per year. It's an unbelievably small number, but it was in beautiful agreement with what Einstein had predicted. The Earth is literally dragging space-time around with it. It's incredible. So from your GPS to that 1919 eclipse to these hyper-precise gyroscopes in space, general relativity has passed every single test we have ever thrown at it. And yet, remarkably, we know it can't be the final story.
And here we are at the great puzzle of modern physics. We have these 2 spectacularly successful theories. We have general relativity, which perfectly describes the world of the big and heavy, planets, stars, galaxies. And we have quantum mechanics, which perfectly describes the world of the tiny and light, atoms and particles. The problem is, they are completely incompatible. They just don't speak the same language. Relativity gives us a smooth, curved space-time, while quantum mechanics gives us a jittery, uncertain world of probabilities. And when you try to use them together, like to describe what's inside a black hole, the math just breaks down completely.
So even though we know general relativity works, we also know it's missing something. It tells us that gravity is the curvature of space-time, but it doesn't tell us what space-time itself actually is at the most fundamental level. What's it made of? Answering that question, well, that's the great quest for physics in the 21st century. And who knows what the answer will be.